ready. Get ready. Get ready. Get ready.
Hello, 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 hello. We already saw a preview of our guest, but we'll invite him in later. So, welcome to the second episode of Complexity Matters. So, who was it who viewed our first recording 317 times? Was that you?
I did 315.
Oh, okay. Yeah, I managed to get through like one viewing, and then I got a little bit annoyed with all the, the speech stop words and my accent. And but no, it was viewed very, quite a lot actually. I was surprised. So
my mother liked it a lot.
Okay.
Yeah, she thought it was great.
That's what you need. So so let's try to do the same kind of segments that we had, and talk a little bit about.
I can remember exactly what I was doing when I heard the news. I was listening to the news.
I have some news. Let's see. Did I already share my own screen? No, I did not. Very, very smart. Here we go. Yeah, so we talk a lot about of course the complex systems approach to behavioral science, but part of that, at least to me, is like the idiographic science approach, studying individuals instead of studying populations. And so recently there was this article, very good article in Quanta magazine. Called "What is an Individual? Biology Seeks Clues in Information Theory," and this is in fact an article about a scientific paper, of course, by people from the Santa Fe Institute, who are using information theory to basically define formally what an individual is in terms of information. So this is the actual paper. So the information theory of individuality. And the reason why this is important, I think, is to have kind of a formal notion about this, is also for behavioral science, is basically we usually say that we are studying behavioral change of individuals, but we don't really have a theory about what that actually means. And this is kind of a technical paper, so maybe we should do an episode on this. I think I saw that our guest Travis was also interested in this, so we might do this. But this requires some study, and it gets pretty formal with lots of formulas and things like that. So very excited about this, and it's relatively new here. March 2020. So did any of you have anything to share? Any news?
Well, this isn't super. Yeah, go ahead, Marilyn.
No, you go first.
Yeah, well, this is related to the information theory piece. It just crossed my mind that there was this another paper. Can you see my screen?
I can share your screen, yes.
Yeah, so it was called Information Theory is Abused in Neuroscience, which was a philosophy paper about and in the Journal of Cybernetics and Human Knowing, where they argued that in neuroscience, at least, they do not define the elements of elements that
you are breaking up a little bit, Matti. you're breaking up. Can you do something about your? You have a robot voice, so
Oh, I don't know if it helps.
Sometimes it helps if you you know, close some programs that might be using the internet.
Well, I don't know if I have anything more to say about this. It was just that there are these things that relate to information theory that you would have to define, like the sender and the receiver.
Right.
Not good?
Right. Interesting. So we'll put the links in the chat. I'm looking at the chat. So we are with like 11 or 12. So more people are popping in. That's great. Or maybe you can put a link in yourself, Matti. Marlijn, did you have something?
Yeah. So yeah, one thing I thought was really spectacular about the individuality paper. When I read the Quanta magazine article, I found that really food for thought. That they say, so we typically we recognize individuals in a way that we like learn what an individual is, like other humans or animals perhaps. But they make this point that from their perspective, individuals may not look like the individuals that we know, and they also suggest some implications for like life on other planets or things like that. I thought it was really fun to think about.
Yeah. Yeah, and also, yeah, a group can become an individual at some point, right? So,
Yeah.
and this paper deals with all those kinds of situations. They come up with different, variations on what it means to be an individual. What I also find interesting, because I've been thinking about this a lot. It might also be interesting to think about what is missing here. So there's kind of there's also something called identity, right? So you have the individual and the individual, and you have the entity and the it entity, the identity. So I think there's a lot of very interesting stuff in here. So we'll probably plan an episode to talk about this paper.
Yeah, I think it also may shed light on this issue of that we always think of complex systems, but when we think of humans as systems within systems with all kinds of subsystems.
Yeah.
I mean, for emotions, but also like physiological subsystems, like your blood flow system, things like that. And they also mentioned, I think, that kind of issue, and so I think it's really interesting for human sciences as well.
Yeah, absolutely. Yeah. There was one thing. I don't know if let's see, where do we? Yeah. So if you know a little bit about ecological psychology, especially in development, this is a very recognizable figure here, and I know this from the work of Gottlieb, right? So and this is supposed to indicate that basically everything is interacting with everything. Very famous picture that's used very often by Gilbert Gottlieb. Strangely enough, they don't cite him, which is always problematic. So in our field, I guess. But it does reflect, I think, the same kind of ideas. And then another paper that is related to this that we might might include in a future discussion is about what does the self mean in biology, and this paper is about the liquid self and how this changes over time. So I think these things are all interrelated and very important to figure out. And I'm glad to see that like the more formal people are also now pointing their attention to this. Hey, Jay says hey. Hi, Jay. Good to see you too. Great that you found us. All right, so let's move to the main topic and introduce our guest. Here we have Travis. Hello, Travis.
Hello.
How are you?
I'm doing pretty good today.
So, how did we meet? I think it was at the conference of the Dutch platform for complex systems, right? And sometimes these things just happen by chance. We had like posters across from one another, and I was like pointing my line. He's using dynamic complexity. we don't know who this guy is. Find out everything about him.
I think that was also one of my first semesters living in the Netherlands, so it was a good timing as well to get connected with you all.
Yeah. So maybe tell us a little bit about your history so far.
Yeah, so I'm originally from the US, where I did my PhD in modeling and simulation with a focus on cognitive science. I got interested in dynamics and complex systems around that time. I was doing a bit of like systems thinking in my master's in human factors, but then really got more into the quantitative side for my PhD, studying team dynamics and problem solving, and did a bit more with that during my postdoc with John Butner, who's like a quantitative dynamical social scientist. Found myself here in the Netherlands now, in the cognitive science and AI department in Tilburg University.
Yeah, great. And you're working with the head of the department is Max Laurens, or is that?
Max is one of the full professors. Peter Spronk's the head of the department there.
Yeah. I met Max when I was in Memphis visiting Rick Dale. He was there at the time. So and they have this great paper where they are using like cross RQA in like a cooperative task. That's where I know him use that a lot in education. All right, so I think let's start your presentation, and then let's see what people who are watching are now 13 people watching. Please ask questions in the chat, and then afterwards we'll have a discussion on. Let's see, how do we get there? Yeah, there we go. So
Okay.
Go ahead.
Thanks. Yeah, so I just want to thank you, Fred, and Marlijn and Matti for inviting me to the second episode. I'm happy to share a bit about my complex systems approach to studying team dynamics. Of course, this is going to be just one example. There's also some great work that's been an inspiration for me from Jamie Gorman, who's been pioneering this area. This talk is mostly based on a preprint, social analytics of team interaction using dynamic complexity, heat maps, and network visualizations. And hopefully by the time I'm done with this talk, you will all know what all of that means. Okay, so I actually like the start that we had to this, talking about this information theory of individuality, because when we think about teams, we know that they're a group of individuals. They work together. They typically share a common goal, although they can also have their own like individual goals. And there's often a high involvement of technology when we're working with teams who are using technology. I think Marlijn was just briefly mentioning that when we think of an individual, there's different levels or subsystems within an individual person, if we want to define the person as the individual in this case, thinking about physiological, perceptual, motor, cognitive, Marlijn mentioned emotion. And this scales up, right, when we think about teams. So whether that's 3 or 4 or 5 or larger size teams, up to organizations. And so this idea about what's an individual is really important, but thinking about different levels within an individual and where you're kind of defining sort of your unit or level of analysis is important. Teamwork and team dynamics in particular seem to emphasize what has been treated as statically for kind of decades of team research, taking snapshots and seeing what you can say about a team, when we know that, forming a team, developing and growing with your team, this is something that happens dynamically, so change is implied. Whether this is due to intrinsic fluctuations of how team members interact or individual processes, or whether there's sort of shifting work contexts that kind of are the catalyst for change in the teams. So one of the things that we typically focus on in dynamics is team processes, and communication is a big one because it's very observable. And we know that communication is something that emerges from interactions between team members. So this is interesting from my perspective as a cognitive scientist, because we have interactive team cognition theory, which stems a bit from the ecological tradition and dynamical systems, and argues that we can actually observe the cognitive processes of teams because it's in their actions and interactions with each other. There's another principle here in a recent paper from Jamie Gorman, which I think is going to be important to kind of unpacking the theory to this approach that we use in our paper. And it's this principle of like local variability ensures global stability, and global stability ensures local variability. So we know at like smaller scales or things that are happening like very close together that there's going to be variation. But for teams to perform well, there should be some kind of global amount of stability. And if that stability changes, then something interesting might be going on. So for this study, it's a case study. I know in the last episode, Merline also talked about data from one patient or one person in their experience sampling. So this is just data from one team. And our goal was actually to try to contribute to team dynamics research by kind of combining several things. So one is use of sociometric sensors, which I'll say more on in a moment. Also combining theory from complex systems on phase transitions, and thinking about how we might be able to sort of bring this to team dynamics work with dynamic complexity heat maps and network visualizations. And we apply this to communications data from a team. So if you're not familiar with sociometric badges, here's an example of the rhythm badges, which we use for our study. These are wearable sensors. You can just put them on like a lanyard around your neck. Typically, they collect things like proximity between individuals through Bluetooth or RFID. They have microphones to detect vocal activity. They often feature accelerometers for physical activity. They're pretty inexpensive, and most people don't know them. If you work at a company, for example, and you already need to wear an ID badge, although me working at the university or home all the time these days, I would obviously notice if I was wearing some lanyard. But what's nice about these two is that they can also be sort of scaled up to quite large scale social activities for longer periods of time. So I'm going to talk here a bit about critical instabilities and phase transitions. Sometimes these are used interchangeably. I'm going to try to make a distinction here. So these are features that are pervasive in complex systems. One of the most commonly referred to example is when we think about how water, for example, might change from gas to a liquid to a solid, that these are phase transitions to different states of the system, and that critical instability might be the period surrounding the transition where there's more variability, for example, in the system, and this can indicate that there's some sort of structural change going on in the organization of that system. So I also have an example here from the Lorentz attractor, which is in one of Damien Kelty-Stevens' papers. If we think about how a system getting started up and establishing stability, what's really nice about this figure is it shows that during earlier phases of this system, if you start generating data with the Lorentz equations, you get some sort of stable level of entropy, which in this case represents kind of the complexity or the amount of order in the system. As the system begins to transition to the more stable butterfly attractor, you see this peak in entropy before it then settles down into a more stable pattern. So what's interesting, particularly with regard to teams, is that if we can identify these periods of critical instability, systems are supposed to be more influenceable during these periods of instability. So if we were to try to give some interventions or feedback, then these might serve as candidate times to do so. And this idea also has been used in psychotherapy in particular for these kinds of daily questionnaires, about periods of instability for patients, and that might be a good time for feedback interventions there. So I'm adapting that here for teams. I'm not going to mention this paper in much detail, but my colleagues and I do have a paper looking at communications and phase transitions in team problem-solving processes, where we look at different semantic codes, which are in the time series here, how we can identify sort of what might be candidate phase transition points. And we did observe that with this entropy-based method, we showed that there were distinct distributions of states between entropy peak points. You can check out the paper here if you want to go into more detail. It's not worth it to say more than that at this point. So in our case study, as I mentioned already, it's with one team. There were 7 people who were in a management team from a large Dutch technology company. They're all sitting around a meeting table, and we had them perform this Lost at Sea survival game. If you're not familiar with this, or maybe you are, there's many variants. There's a lunar survival, there's a desert island survival. The principle is the same, that there's a list of items, and as an individual, you first have to rank these items in terms of their importance for your survival. And you have to afterwards work as a team or as a collective to agree upon a final ranking. And so this involves sort of, you have to think about your rationale for why you think having a shaving mirror might be more important than having water. You know, maybe you can use the mirror to light a fire or something like this. And then you could purify water, for example. So maybe it's more important than having water. That's just one idea. We had the participants wear these badges, and they completed some questionnaires, which aren't in the scope of this talk today. So we had a couple predictions. They're relatively straightforward. One is that if we use this measure of dynamic complexity, which I'll elaborate on soon, we should be able to recover known task transitions. So periods in our observations where we know that what people were doing changed, as well as what we would call identifying unknown event or interaction transitions. So this is something that we didn't know necessarily was built into our data collection scheme. We also predict that we should observe changes in the network structure in the periods between these transition points. Okay, so rhythm badge data, we use the vocalization specifically. This doesn't store any of the audio. Actually, it only stores like volume or amplitude, which you could see a visualization of here if my mouse shows up. We apply also a vocal activity or voice activity detection algorithm, so we can see sort of who's speaking for each 1 second interval. For dynamic complexity, this is a method developed by Gunther Schiepeck and his colleagues. And this is argued to serve as an indicator of system instability, and I'll say potentially a phase transition. It's the product of 2 computations. One is fluctuation, which can be thought of as how intense the fluctuations are between the range of values. And this is also a windowed measure, so it's within a given window. And also distribution, so how much deviance there is in a window from sort of a uniform or an equal distribution across the total measurement scale. So both of these range from 0 to 1. You take the product of the 2, and you have the sort of dynamic complexity of the system over time. And we apply this to the vocal amplitude data. Maybe this is a bit more detailed than is necessary here, but I think it's important to point out when you're doing complex systems or time series analyses, parameter selection is often really important. And we did some parameter search here to see what would be sort of viable parameters after we already sort of thought about reasonable ones. We wanted to explore this a bit further. So we used like the known transition points and calculate different ranges of, for example, the windows for dynamic complexity, resampling intervals, windows for instabilities. I don't think this part's in the preprint, but we have an updated version that's under review now. But in the long story short, we did select reasonable parameters. You could actually maybe choose better parameters that optimize for accuracy for known transitions, but then we might be losing out on these sort of emergent transitions that we were interested in. Okay, so here we are for the dynamic complexity heat map. What you have here on the left side is dynamic complexity for each of the participants. They just get a letter. And then you can see the dynamic complexity value over the course of the interaction, which ranges here from 0 to 1. On the top part here, we have sort of what we saw as our known transitions, right? So changing from pre-task to individual task to team task to post-task. Down here, we have the average dynamic complexity across the team. And then we have these points that we identified as critical instabilities at the team level. So this was windows where there was greater than 2 standard deviations from the mean for those dynamic complexity values.
Sorry, Travis.
Yeah.
So it's dynamic complexity of what in the individuals?
Yep, sorry if I skipped over that. So this is applied to that vocal amplitude data. So it's on the communications, and it's basically, you know, the loudness of the voice with some filtering as well. Yeah, so you can see, for example, you know, whether there's periods where there's not much complexity of the signal versus where there's a lot going on, and you would expect more, obviously, during the team task here. And I'll unpack this a bit more as well. But what I think is worth pointing out here was that with this method, we were actually able to recover these sort of points of transition that we knew beforehand, and 2 sort of emergent transition points, one during the team task here and one during the post-task period. So we took, I'll just go back real quick. So we take the time periods here for these transitions we detect, and we slice up those voice activity detection data, which is just who's speaking or who's not. And we can calculate a couple measures based on that. So in this case, we have nodes, which represent each of the speakers and their individual utterance rate, so how much they're speaking during that window that we identified. And then also the pairwise response rate, so how often pairs are sort of responding to an utterance from another person, and that's the thickness of the line. So in this case, we showed sort of that, okay, well, we know that there's some transition points and we identify some emergent points of instability. We can slice up the vocal activity for those periods and look at the network visualizations. And here we see something like, okay, well, there's some more activity going on here. Now they've switched to the individual task. There's not much going on. The lines are really thin. The nodes are relatively small, except for this one. And sort of visually, you know, this gives some intuition about that there might be some changes. So for example, when they first start out, all of these lines are almost equally bold. So they're all responding to each other. Whereas here, there's a bit of a change. This person's contributing less and less after other people. So what do we get from this?
Just a moment, Trevor. Just a moment. Yeah. So James is asking, so each ABC, etc., is the vocal data of a team member, right?
That's correct. Yep.
Yes.
So in this case, the nodes are representing the individuals of the team, and the nodes in this case are actually the sort of voice activity detection. So it's how much they're speaking, whereas the dynamic complexity is actually applied to the amplitude data itself.
Okay, right. So Krishna says volume and amplitude of each team member. What does IIRC mean? I don't know.
Not
Tell us,
sure.
Krishna, what do you mean?
If I recall correctly.
Yes.
Okay, yes.
Of course. Thank you. Thank you. Yeah, I'm not a boomer, but in this case, you would probably say something. Continue, please.
Yeah, I just got a couple more points.
Okay.
Apologies, this is cut off a little bit. But so, you know, one of the nice things about this is, well, we can take the sensor data and then we can see where things are kind of happening, where transition points occur, how networks change. But ultimately, we have to go back and try to make sense of, well, what was that transition we saw during the team task? is it anything of importance? In this case, it was actually a point where a team member who hadn't been contributing that much added a novel perspective to the rankings, and then many sub-conversations ensued after that. So there was kind of a flurry of activity based on this point. So it was actually an interesting change in the team's interaction. And then there was this last one during the post-task, and that was actually where the facilitator started to go over the rankings, sort of the expert rankings. That was a point that I skipped over earlier. So in this case, I believe it's like Coast Guards actually rank the items of importance for survival while being lost at sea. In the lunar survival, you have NASA engineers that do that and so on. So in these two sort of emergent transitions, there was actually some interesting interactions that were occurring. Just my last slide here is we set out to sort of show that maybe there's a novel combination here of sensors and theory and visualizations that might be able to give some insights for team dynamics. We wanted to try to provide this sort of empirically derived means of identifying transitions in these dynamics. But still we need kind of manual efforts to characterize sort of what that transition was or to qualify it. We do still think that this has potential for some kind of real-time or near real-time feedback systems, providing a debrief afterwards, saying here's sort of a heat map and network visualizations, and that kind of scaffolds sort of what kind of takeaway points you might have from a given task or training session, especially with regards to making sense of communication patterns. And then, of course, this was a case study. So thinking about how or if to scale the method, part of the work that we do is idiographic in the sense that these dynamics might be specific to these teams in this context. So why would you try to generalize? But there might be some more robust types of transition patterns that we could detect that might indicate, who performs well, what teams will perform well with this kind of task or not. That's still an open question. And then the context was pretty specific, sitting at a table doing this task. We didn't take advantage of movement data or anything like that yet. And I think that's where I'll end, and just thank my collaborators, without whom this work wouldn't be possible, and of course thank NWO for funding. And I'll turn it over for any additional questions if there are any. Thanks.
Okay. Well, thank you. Thank you. I will just share my screen here. So this is the preprint, right?
Correct.
Yeah. Okay. So, well, it's in the description, but I'll also post it here. Preprint for the people. So I don't know. Maybe it's a good idea. I don't know how familiar everyone is with this measure of dynamic complexity. So I have here this nice graph that I always use to explain this. So anyone who's watching in the chat, if you have any questions, please post them. Martin says, thank you, Travis. Really neat.
Thanks, Bart.
And then we'll discuss them. But maybe it's interesting to would you like to say something, Melanie?
I have a question.
Oh, you have a question? All right. Ask your question.
Yeah, I could ask multiple, but I have one related to the dynamic complexity, and that is, so I imagine with this focal amplitude data that you have quite a lot of data points. So I wonder why did you choose to use dynamic complexity and not some kind of entropy measure or something?
Yeah, that's a good question, and I think it had to do with trying something other than entropy, which, well, Shannon entropy you would apply to categorical time series as well. But we wanted something that we could actually apply kind of maybe uniformly to the different types of data streams we would get from the badges, which we haven't done yet. Our plans were a bit derailed by, this COVID pandemic that happened last year. So, and there was a point that I also skipped over there because with the vocal amplitude, you also get like a large amount of variability. So we did also resample this to sort of minimize some of the fluctuation a bit for sort of breathing noise versus, you know, someone speaking excitedly. So I think, yeah, that's the main reason that we wanted to try this measure for something that would be able to apply if we have, you know, something from movement and vocal amplitude, or even just speaker-only data, which would be categorical.
Yeah. So James is asking here, the edge weights in the networks are mean dynamic complexity.
So that's so. Let me clarify that, because the networks are based on the voice activity detection, which is not the same as what we applied the dynamic complexity to. The dynamic complexity only tells us sort of at what time points in the time series to take for these network visualizations, and then these are based on the sort of the amount of vocal activity. The edges are the pairwise sort of utterance rate, so how often pairs are responding to an utterance of the other. And it's divided by, I think, the total period of that time or something like that.
Okay, yeah. Okay, here's an interesting question by Jay Holden. I wonder if measures of oscillatory entrainment, I think he means here, that's autocorrect probably, such as relative phase, could be used to assess coordination between pairs of participants.
Nice comment from Jay, thanks. Yeah, so in another project, we are actually looking at a variety of multivariate coordination measures. I think we were thinking about some of the like cluster phase as opposed to just a bivariate relative phase. But I think that's actually an open area that my colleagues and I are also actively exploring, like whether like looking at pairwise synchronization, or whether there's some more informative team level synchronization that's useful. But I hadn't thought about applying this specifically to the amplitude data yet.
Yeah, I think you can retain a lot of the let's say the we can retain the continuous signal. I think with a lot of these techniques. Yeah, I think it would be nice to sort of get to this group level in a different way than comparing pairs. I would say, but maybe that's does a thing like that exist? Multivariate coherence?
There's a cluster phase synchrony. Although
right. Yeah, of course. Yeah.
One thought that comes to mind, though, with regards to speech signals is that there isn't inherently a lot of synchronization, right? We're not sitting here talking over each other, or you know, we're not singing together or something, which is when you would see more synchronization. So you have to think usually more about like turn to turn coupling or something like that. Yeah.
Well, I have done some studies with audio and then recurrence analysis between two participants, and you can get like, of course, recurrence of amplitude values or like tone sweeps and stuff like that. But no, that's true. Yeah, you don't have really a. It's not like a heartbeat or movement or a signal.
Yeah, I was also thinking of the movement data that may come in there. I already have the impression that in this live stream we're a bit nice swaying from left to right. So
yeah. What kind of movement data did you have in this study?
So in the badges, they have what's kind of like it's an accelerometer, but you get like a degree of offset. So so it's similar to the postural data. We haven't done any efforts yet to sort of validate how accurate it is, but we're looking into things like open pose to sort of calibrate the data from the sensors and seeing how that's sort of aligning with postural sway, for example.
Yeah, because people were like, when they're doing this task, are they sitting down? Are they?
Yeah, and this one they're sitting at the table.
Yeah.
Yep.
Yeah, that might be a bit constraining for the movements. That's something we also have done when putting people on like a Wii balance board, for instance. But then we made kind of a mistake by putting them also behind the table, and that's that sort of fixes, well, at least one or two movement directions. So, but these badges, they're wearing them like on a
Yeah, so around the neck, like
around
in
the neck, right?
picture.
Okay, yeah. Well, yeah, it would be interesting. Might be an interesting tool also for our lab to think about. Yeah. All right. So let's see. I think we do not have a question in the chat, but
Well, I have one question. So do you see applications to, for example, lifestyle counseling sessions or therapist-patient sessions or doctor-patient consultations? Anything in that direction?
Yeah, so this idea, when Gunther Schiepek developed it, it was originally applied to, I think, first like patient self-ratings of different dimensions related to their therapy process, and showing these kind of heat maps to act as a scaffold for the discussion for the therapist, for example, to say, okay, what happened last week on this day, because there was some critical instability, particularly in your questions relating to emotion or something like that. So I think that that's an idea where, at least for like therapeutic interactions, it's being developed and evaluated in some cases, at least by Gunther and his colleagues. So I think here, the idea was to adapt that idea for something like teamwork. But I think the point that you make, Matty, is also true that, well, I haven't really seen it applied to the communications data in psychotherapy work, for example. So it might actually be a bit more less intrusive, I guess, right? Because you're looking at just the interaction. Although I guess there's this zooming challenge, right? Of, okay, well, is it applied to just the periods where you're interacting with the coach or the therapist, or is it being applied more broadly across your day-to-day when you have some kind of wearable sensors, for example?
And also, there's been a huge rise in the demand of e-therapies. So you could actually just record the a therapy session that takes place over the internet, and you also have the group therapy sessions. So there might be some interesting applications in that direction. Or the Complexity Matters podcast, you could see whether there are transitions going on here.
Yeah, well, I think that's something that businesses are always thinking about, right? So what kind of information can we get from people sitting behind webcams using interface like the mouse or the trackpad or stuff like that? Well, I mean, it might be a bit technical, but I think one of your last points was, which is of course not here, but was about doing like a real-time, was it intervention or was it like real-time?
Yeah, so the idea is just that if we know from complex systems theory or dynamical systems theory that periods of critical instability are when we have sort of the potential to influence a system the most, then we think that with the data, the way that it streams from the badges, the relative efficiency of these computations, that this might be something to investigate in future work as some kind of feedback system, right? But what can you say? So you could say, okay, you're sort of maybe near a transition point because your communications look less stable than before. So we see this as kind of a flagging point in future work to sort of see what kind of feedback or intervention should be delivered at that point.
Yeah. No, I'm just looking here at the time scale. So because what you need first, to fill out this window, right? And then you can calculate the dynamic complexity. And in fact, if you want to have the mean complexity, so you need, let's say, this entire column to be able to decide whether right? You're dealing with a critical instability, but this is actually like minutes, right? So that should be possible, I guess.
Right.
Yeah.
And I mean, so we did balance like the window sizes here, and also with that in mind, that smaller windows would be able to be a bit more efficient, a bit more near real time to be able to give some feedback if we were working towards that.
Yeah. So the reason I'm asking, I'm thinking about what is actually the advantage of using a continuous signal like speech or movement, perhaps, because we are used indeed to use these, at least dynamic complexity measures, just looking at questionnaires, which you can't ask people to fill out response every second, right? So that's indeed a great benefit that might be interesting to think about some more. And in a therapeutic setting, I don't know. You could also think about. We've done also some studies with like the movement energy analysis, those kinds of things. So
it's different kind of scale that you're then interested in. But
that's true. Yeah.
You could also think of coupling them, of course. Yeah. I also have one more question, if that's okay. Yeah, that's outside here. Sorry.
Someone broke out of their lockdown.
We have a drive-by supermarket.
Oh, that's it. All right. Yeah. You're in the jungle somewhere.
Yeah, somewhere in the jungle. I was so I really like this like more fundamental idea maybe with the networks, that you determine stable periods in the time series in order to visualize the networks. And it also makes me think of those psychopathology networks of self-ratings data. Because if you would make a network in a period in which there is such a transition, then you kind of get a nonsensical image of what's going on, because it's an aggregate of two stable networks. So I was wondering what you think about how this idea could generalize, and also how you could maybe test it with some kind of surrogate network or something like that. Yeah.
That's a great question, and I think part of why I mentioned my other paper in CogSci earlier was because there the idea was that when we identify the transition points, we ought to be comparing what occurred between transition points to say whether they were distinct or not, right? So if a system was moving from one state to another. I think that something similar could be applied here as well for values or network representations, but obviously with more data. I do recall my colleagues and I talking a bit about some kind of surrogate testing here as well, to see if there was distinctions between the network visualizations if we just shuffle the times and identify random instability points. Although we haven't gotten to that point yet, but both seem like good avenues for future work.
While on the subject of the networks here, was it the case? I don't remember. Did you also calculate like network measures of these based on these things?
No. So the only measures are that go into the visualization. So like the amount that someone's contributing and the edges. We didn't do anything else yet.
Yeah, because you could also compare to non-critical transitions and look at the structure of the network and then figure out if they are different or if they're different right before. Yeah. And can you pinpoint now based on what these? No, I guess not. But which one were the emergent transitions? Do you?
Yeah. So the emergent ones, I think, is this. One sec.
Want to share your screen?
Yeah, that's fine. Right. So the emergent ones is here. This one in the team task and the post task, which corresponds, I believe, to this one here, and I think this one.
Yeah, so it's not quite obvious from the just looking at it.
Right. But so I think this one, for example, was that period where there was a lot of activity during the team task after some initial activity.
Yeah.
Yeah.
Okay. Well, so Martin had still a question which is probably related to what I was saying about the real-time application. So there must be some computational, about the real-time. So, well, in my experience, it doesn't. Yeah, it takes some time to calculate these things. What do you think? Is this a problem or?
Well, I think it's a trade-off, and that's also why I added real-time feedback / debrief. So I think maybe as a first step, it might be useful to just do this like right at the end of say a training session or a team task, see how these kind of visualizations might be a good tool for debriefing teams. And then trying to scale that up to streaming the sensor data. I mean, the sensor data is already streaming to the laptop, which is why it's seems like a good candidate for this kind of system, but with some testing for the computation time.
Yeah. So Martin is also. I think this is a little bit what I suggested, but. Any thoughts on comparing networks from the emergent transitions versus possible transitions, pre-individual group and post-stages? Yeah, I think that maybe you're already doing something like that, but I think that would be very interesting. Yeah.
And I think that was kind of what we had aimed for, something like that when we had a larger scale data collection plan.
Yeah.
And in this case, we ended up with one team's data before we had to.
Had to stop.
Yeah.
Well, that's too bad. But well, it serves as a very interesting proof of principle, I guess. I'm also thinking about once you can do like more experimental stuff, trying to invoke transitions, those kinds of things. It's an interesting paradigm, I think.
I also really like the known transitions part, as you explained it, because then you get some kind of control about that the dynamic complexity is working there. So I think that's super interesting and also something to think about. For example, in psychotherapy, when someone starts or maybe is close to the end of psychotherapy, that may also function as a known transition. So. That's interesting, I think.
Yeah, these oh, so I think in these tasks you have these it's the same like with the insight task, right? The insight and problem solving task, which also has these that a number of things can actually happen, which is helpful, because if you start looking for, peaks or changes, you'll always something. So it's to have this this idea about some things must happen, right? Okay. So any more questions? In the chat we had like at the peak we had like 22 or 23 viewers. Yingmeng has a question. I'm wondering, do you think it's meaningful, helpful to build some formal models about it? Very good question.
It is a good question, and it's something that I struggle with a bit. For example, there's some really nice work by Mengs and Zhang adapting like the Huck and Kelso-Buns model for looking at group rhythmic behavior, and that's a nice formal model that describes that kind of behavior. And I'm struggling a bit to find what's the equivalent for sort of non-rhythmic, very dynamic team interaction data, especially with so many different modalities. So some of my colleagues are looking at more smaller problems like, okay, well, what does it look like for groups with postural sway data? Or if we take some kind of vocal amplitude data, is there different kinds of models that we could use to both simulate some of that data, how it would behave under different conditions versus the empirically collected data. Although that's something I think kind of a hard problem right now, but something that's definitely needed to be able to have a bit more control and testing some of these things, with data from the models.
Yeah, there's of course the well, a lot of people would go to agent-based models, right? But if you're like if you have like what is it, 6, 7 participants or units that might interact, yeah, I think you could still, well, yeah, you could probably still work with the coupled differential equation setup, I guess. I'm thinking about the people from, I'm actually not sure where they are right now, but the people who study like the synchronization in music performance. I think Mike Richardson did some. That was like in the rocking chairs, but they've expanded it to different domains. And I think drumming together. I've seen studies on drumming together. And also models. So you like coupled oscillator models that are.
One of the things that's really nice about those, I think I was reading a paper by Peter Keller recently, who has this kind of model where you can generate, even have a virtual agent that will sort of kind of create rhythms together with humans.
Yeah.
And there's like an anticipatory component, self-correcting component, and things like that. But then I think it's often going back to this, assuming rhythmic behavior, you can make pretty good and robust models. But when things are not rhythmic, that's where I think the real challenge is. We don't have good models for that yet.
Mm-hmm. Do you know this the reference for the group rhythmic version of the HKB?
Yeah, it's Mengchen Zhang and Emmanuel Tognoli.
Yeah, maybe
I can maybe put it in the chat or just pull it up here.
Yeah. I'm not sure if you can paste a link, by the way, but you can.
She has this repository here for the data as well.
Uh-huh.
I'll find it and
yeah, and we can post it in the comment to the video. That's also possible. Yeah. So and I'll also look up this the music, the rhythmic drumming, because I think they were using some kind of coupled oscillators thing. I think, Marlijn, you also saw Scott Kelso's presentation, right? On the, I think he was also talking about something like this.
Yeah, he talked about this model at Conference for Complex Systems.
Yeah.
So he talks about it like that this HKB model only works for a diet. And he has this Kuramoto model for really large groups.
Yeah.
And then it goes somewhere in between there.
Yeah, there's a kind of hybrid model between HKB and the Kuramoto neural oscillation model.
Yeah, I think they even show its equivalent for this small group.
Oh, okay.
Travis knows that better. But yeah.
I think it's the same work as I think Mengchen worked with Scott Kelso.
Yeah, probably.
Yeah.
It's the same group, I think. Yeah. All right. So let's see. The chat is talking about ice cream car perturbations. So maybe this might be a good point to round up here, because we've been streaming now for an hour. Oh, it's good time, I think. So thank you a lot, Travis. We'll do our final segment, which is the strange attractor segment, and I actually managed to.
It's very strange. Yeah.
yeah.
But attracting. Yeah.
It's a bass lick I recorded according to the file like 10 years ago or something like that. So I thought it might be appropriate here. Yeah. So this is our segment where we do. You can promote anything you like, recommend anything you like. Does anyone have anything?
Yeah, I have
Yeah.
2 things.
Two things? Should I... Yeah.
Can you share my screen?
Is this yeah.
Yeah, so the New England Complex Systems Institute, they canceled their winter school, and but they created a virtual session, which is 15 recorded talks by Yanir Bar-Yam and I think some other people. I'm now going halfway through, so I'm not completely sure what's to follow. And then they also they provide like 4 question and answer live sessions with Yanir Bar-Yam, which might be quite interesting for many people. And here are the topics of the course. Oh, it's 12, not 15. I thought there were 15. Okay, anyway. Yeah, so these are quite fun and very, very interesting perspectives to the implications of complexity into social systems, for example. And then I also wanted to show this, if anyone is unfamiliar with Nikki Casey's interactive introduction to attractor landscapes, this is just like 5 minutes, and this is an awesome demonstration. You have like these different sliders that they talk you through like what's going on, and then you have like so for example here, if I release fish, it goes back to the equilibrium, and then if I catch fish, but if I catch too much, they die, and then I can't go back. So yeah, but there are quite many demos and explanation of how the attractor landscapes work, and this is like it's a superb demonstration, and it's very short. I really recommend that.
Oh, cool. Yeah, looks great. Did you have anything, Marlijn?
Yeah, I have one paper.
Yeah.
Is my screen shared now?
Yes.
Yeah, so I'm having a bit of a promotional campaign for this paper because I think it's really, really great.
Mm-hmm.
It's by Paul van Geert, who did a lot of complex systems research, really a pioneer. And he wrote this article, and I think it's just a wonderful introduction to dynamic systems, but also, if you're already quite familiar with it, it touches on many important issues for behavioral science. Here you can see the index. So it also talks quite a lot about causality and how to think about causality in complex dynamic systems, which I think is really relevant and often not mentioned so much in other introductions because it's so complex. But he explains it really clearly. So it's a big recommendation, this article.
Yeah, it's an excellent paper. Yeah, maybe we can ask Paul to be a guest at some point when we get like hundreds of viewers.
Yeah,
no, I think he'll be glad to talk about this. Great. So yeah, put a link also in the chat or maybe in the comment. Did you have anything, Travis?
Yeah. Can I?
Where is your screen? I lost your screen.
I stopped sharing. Sorry.
Yeah. If you share it again, I can add it.
Yeah. Is that working?
There you go.
Yeah, I mentioned John Butner's work earlier, who I did a postdoc with at the University of Utah, and he's written a nice book that he published for free himself. I think in 2018 it came out. What's nice about this book is it's written towards your sort of typical social scientist, assuming that you have some basic understanding of regression and how far you can get with regression and doing things like changes outcome regression to understand attractor dynamics, and scaling up beyond that to get to the point where you understand chaos and fractals and multivariate coordination and things. Starts really simple and nice, especially understanding time and perturbations and how that influences a system, and scaling from there. So this is a great resource, so I recommend it.
Excellent. Yeah.
Well,
Great.
that looks really interesting. Yeah, thanks.
So do you think it's something that could be used like in an introductory course, or is it more like a
Yeah, I think he's written it so that it could be used in an introductory course. I think there might be a point where you need a bit more than regression, like multi-level modeling or structural equation modeling, but that's in the later chapters.
Okay, interesting. Thank you. Yeah, well, I had let's say, yeah, maybe just this is a little bit of a promotion. So we had a summer school in the before times, and now it's going online. So so this year we last year we did not do it, but this year we're going to offer it online at a greatly reduced price, might I say. Especially for students and PhDs, and it's complexity methods for behavioral science, and you'll learn all about hands-on techniques for analyzing time series basically, and using complexity measures. Matti followed it, and Marlijn was an instructor, so it's it's a great course, and it's completely online this year. So if you're interested, you can have a look at that. But actually, I wanted to point you to this YouTube channel. I don't know if you ever, you want to
I just wanted to say that was one of the best courses I've ever taken. I really enjoyed my time. I've been doing EMA, like momentary assessments, answering a questionnaire, and then when I look at my mood over 2 years, there's like this huge peak that goes on and on. Oh, that's when I was in Radboud. Yeah.
Well, that's very nice of you.
Yeah. So you should have a program for discounts for people who were in the previous sessions, so that they could come in for cheaper.
Come in again. Yeah. I don't know. Maybe you can present something, be an instructor. You know, and by now you have you have some publications and some data you could talk about. So yeah, we can work something out. Well, thank you. Thank you.
When is this being held again? Sorry.
This is now in so the date has to be confirmed yet, but it's in the beginning of July. I think it's the first week. Yeah. So this page will be updated. It's now a little bit boring, but yeah. So it's a summer school. So I very often look at the videos by Sabine Hossenfelder, YouTube channel you see here. And she is a physicist, and she makes these really short, it's like sometimes it's like 6 minutes and 10 or like 15 minutes about a lot of different stuff. It's mostly physics, like questions like, is infinity real? But there are also kind of timely topics, like for instance, I thought this one was very interesting. All you need to know to understand 5G, because we know, people are like destroying these these 5G masts. I don't know if that's the case in Finland as well, but here it is. But if you look at her video, she of course gives a physicist's perspective on what radiation is and those kinds of things. Maybe those people are not that crazy. You of course should never destroy other people's property, but there's not a lot known about some of the aspects of the 5G radiation. Also herd immunity, for instance, but she also discusses stuff like where is it? Warp drive news, for instance. And when she has a video about warp drive news, you better watch it, because then it's real. But she also talks about complexity stuff, and this is very interesting. If you want to get started, look at this one: path dependence and tipping points, where she, I think, in just like 11 minutes explains a lot about phase transitions, and here she uses the example of chocolate, which you for instance, have left too long in the closet, right? You didn't eat it, and then it gets this like gray or a little bit white color, right? It's not shiny anymore. That's actually, you can describe this as a phase transition. So that's a very I'll put it here in the chat as well. Very informative, and all her videos are like that. So go check that out. Yeah, for me, that's kind of all I wanted to say. Maybe we can say something about the next episode. I did very quickly make a banner, but we don't have an actual confirmation. Where is it? Oh yeah, I have to remove all all our. There we go. Yeah, you can see it. I should do this using a picture. I've now made it the background, so we can't see it. But maybe you can say something more about it.
Yeah. So Gwen Marchand is going to talk with us on probably the 18th of February, somewhere in the late afternoon, because she's in Las Vegas and we're in Central Europe, so we'll figure it out so no one has to stay up all night. But anyway, so we're going to talk a bit about like networks, implications of complexity to motivation and engagement, but a lot of it is still in the shroud of mystery because, of course, Gwen will talk about the things that she will find most interesting at that time point.
Yeah.
She's
but
been
it will
doing
have to do something with education and right, or learning and yeah. Well, it's very interesting because not a lot of people are doing research on that, so I'm very curious to learn what she has to say. All right, so I think that was episode 2. Thanks a lot, Travis.
Thank you.
And yeah, maybe we can talk again. I read that you were also interested in this paper about the individuality.
Yeah, definitely.
Yeah, so maybe we can plan an episode to talk specifically without the guest, but then to talk specifically about that paper, because I think it's quite it's not an easy paper.
No.
Yeah. So okay, so goodbye, and till next time.